what do we mean by curve parameterized by a path? Okay. And then we said that if you have a path or a parameterization of a given curve, then that parameterization should satisfy some conditions. For example, it must be piecewise smooth, it must be piecewise regular. Okay. And then we talked about orientation preserving curve, or maybe the reparameterization. Okay. So you can reparameterize the curve so that a curve can have different parameterization. Okay. And you can switch between parameterizations. Okay. And then you must have, so if you want to switch between the parameterization of a curve, then you must have a map phi actually, phi. Okay. That phi allows you to switch between the parameterization actually. And if that phi in addition, okay, is I guess increasing, I think.
Yes.
Then
Monotonic
and increasing many. So condition, it has certain definition, condition that it must satisfy, but in addition, so if phi is, I guess, so when a curve is parameterized, but it's an orientation preserving curve actually. So when a curve is orientation preserving, okay. So curve is going to be orientation preserving, okay, if you have phi that are taking you from one parameterization to another parameterization, should in addition satisfy a condition, and I think that condition was what was that condition? That condition was increasingness or smoothness. Of a strictly increasing. If it is strictly increasing, okay, then it's going to be an orientation preserving parameterization. Okay. So whenever you are talking about a curve is a subset in Rn. Okay, it's an image of a path. Okay, P. That path we're going to call it parameterization. Okay. And that path should additionally satisfy some condition like piecewise regularity and piecewise smoothness. The next thing that I would like to talk about today is something what you call the curve segment. That okay, you have a curve, but somehow you are not interested in the entire curve, but a part of a curve actually. Okay, and if you have a curve segment, we're going to call it a curve segment. Okay. And then we're going to say that okay, if you have two curve segments, how you can join them and make a third curve out of it actually. So we will call it a concatenated curve. Okay. So taking two curves and creating a third curve out of it. So here's a definition of a curve segment. So a curve segment should be something like this. That okay, it's a part of a curve, okay, and it must have endpoints, okay, and so if this point is, for example, A, then this point must be P of A. If this point is B, then this point must be P of B. And in addition, if this curve has an orientation, okay, so it goes one way or other way, okay, then you're going to say that this point is the initial point of the curve segment, and this point is the terminal point of the curve segment actually. Okay, so what I said, so I would like to put it in the form of a definition actually. Okay, so what's a curve segment? So imagine I have a curve C. Okay. Obviously, this curve C is a subset of Rn, and it's parameterized by a path. So whenever you hear of a curve, you always ask, okay, what is the parameterization of this curve? Okay, so parametrized by a path, by path map P from I into Rn. Okay, where I, if I is like a closed interval, okay, then so if I is an infinite interval, you're going to call it a curve, but if you restrict it to be a finite interval, then the same curve would be called a curved segment actually. Okay, so I have a curve with a parameterization P, where the domain of the parameterization R, the path, is a finite interval, okay, a closed interval. And such a curve is called a curved segment. Okay, it's called a curved segment. Okay, and what else we can say about this curved segment? That the P of A, which I am say denoting by A, okay, maybe A star, say, for the sake of simplicity, to differentiate between this A and this A, and B star, which is P of B. These are the endpoints. Okay, endpoints of curve segment. How does the curve would look like if this P of A is same as P of B? Bounded. Point. No. So imagine I have a curve.
Loop बन जाएगा, close हो जाएगा.
Yes, so it's going to be a loop actually. So if the terminal point and the initial point are the same, so you started from somewhere and went on and returned back, you're going to call it a closed curve actually, or maybe a closed loop. Okay. You're going to call it. Then C is closed curve. Okay. You can also call it loop. Okay. And moreover, if C is oriented, okay, if C is oriented, what do you mean by oriented? That every phi that reparameterize it must be an increasing map. Okay, must be increasing map. If the curve, if C is oriented, then you can say that this A star, which is P of A, is initial point of the curve, okay, and this P of B that I am denoting by B star is going to be the terminal point of the curve. Okay. So by a curve segment, you mean a curve whose parameterization is defined over a closed interval. Okay? That's what it is. What do you think? What would be the reverse curve segment actually? So this is curve segment. So what would be the reverse curve segment?
Change हो जाएगा सर, terminal initial हो जाएगा.
Yes, so everything would change. So terminal point will become initial point, and initial point will become terminal point. The orientation will be changed. The P will become P bar. Okay. So the P bar is going to be defined in the terms of inputting the negative values into the P. In other words, P bar, so P bar of P. So how can I find, for example, the negative parameterization of a reverse curve is going to be the take your P and substitute minus T into it, for every T in the interval I actually, and you can get a reverse curve. Okay, and everything but the reverse. So I'm not writing all that stuff. ठीक है जी?
Sir.
जी.
Sir, negative का मतलब ये negative value नहीं है, उधर direction.
So take the values from the interval t, and instead of substituting t, substitute minus t actually. Okay? So what you're going to get? So think about it. वो जो t पहले आपको was, so for example, if the p of a was giving you, what do you say, p of a, okay, but if you're going to substitute, p of minus a, where would be that p of minus a actually?
At the point of b.
At the point of
P of b.
p of,
B.
are you sure? P bar की domain क्या होगी? So the domain of the p bar is going to be कहाँ से कहाँ तक? I bar. So I bar is what? So it's going to be negative a to negative b to negative a actually. Okay. So you just reverse it actually. So you have this line, just reverse it. So everything would be reversed actually. The rest of the things are same. Just the easiest way to do it, if you don't want to change interval and everything, so you just say that, okay, if you want to find the reverse parameterization, just substitute for every t minus t into your original parameterization, and you will get the reverse parameterization. So imagine I have a curve p of t, okay, that looks like, say, sine t, cos t, and t square, where the t is from the interval 0 to 2 pi. Okay? So is it a curved segment? Yes, it's a curved segment. Okay? So what would be the initial point of it? In space? Initial point क्या होगा? 0, 1, 0. Okay, the terminal point is going to be 0, 1,
4 pi.
4 pi. Okay? And what would be the reverse orientation of it? Yeah, reverse curve for it. So you need to do p of minus t, and the p of minus t is going to be minus sine t, cos t, and t square. So that will be the parameterization of the reverse curve. Okay. Alright, so if you have an oriented curve, then all such things exist. Initial point, terminal point, curve segment, and the next thing is, imagine I have two curves like this. So that's a curve that is defined on, and for example, interval, say a1 to b1. Okay, and I have another curve that starts from here, the same point b1, and goes somewhere actually. Okay. So I'm saying that imagine this B1 for such a curve is A1, so A2, and it is defined on ends at, for example, B2. Okay? And what is the key thing? At this point, you can see that this is kind of a shared point between the both curves. So I can say that the P of B1 is same as P of B2, or maybe if this is parameterized by P1 and this is parameterized by P2, so I would say P1 of B1 is same as the P2 of B2 actually. They both can have an orientation, okay? Not necessarily this kind of orientation. This guy can have a reverse orientation as well. Okay? They are going to have an orientation. So what I would like to do, I would like to treat this entire curve as a single piece actually. I want to treat this curve as a single curve actually. I don't want to treat this curve as two curves. So in other words, I have curve segments. I want to join them if I want and create the new curves out of it actually. Okay? And this process of joining two curves is essentially called the concatenation actually. So it's like concatenation of curves. Okay? Have you heard of word concatenation?
Yes, sir.
क्या होता है concatenation?
Catenation
So जो कार्बन कार्बन बॉन्ड केमिस्ट्री पढ़ा जो कार्बन कार्बन की बॉन्ड होती है सेम कार्बन मिलते तो
प्रोग्रामिंग में भी पढ़ा होगा concatenation. So when you write, for example, 32, number 32, what is the relationship between 3 and 2 actually? So when you are writing it, what you are doing is that you are concatenating 3 and 2 actually. So you see it as a string actually. In which you are taking 2 digits, you are concatenating them and getting a number. Anyway, a number of ways to make sense of this. ठीक है जी? How to precisely define the concatenation of 2 terms? That's what is our next objective. Okay. So here's a definition. I'll do an example of it. Then this will be the last thing about the curve. And then we'll talk about some other properties of the curve. Okay, so imagine I have 2 paths, Pi, where I is 1 and 2. Okay, and the Pi's are the maps from Ai and Bi's into Rn. Okay, so there are 2 parameterization, which are parametrizing 2 curves, say C1 and C2. Okay, and these 2 parameterizations satisfy, what condition should it satisfy? That at their endpoints their values agree actually. That is, P1 of B1 is same as P2 of A2. Okay, so this is what condition that they satisfy. And these are the parameterized parameterizations of the curve, say Ci. ठीक है, Ci is C1 and C2 respectively. ठीक है जी. So if you have 2 such curves, you're gonna call 2 such curves that these are 2 adjacent curves actually. So this curve is adjacent to this curve. ठीक है. Now I would like to do what? I would like to give this endpoint a name A. Okay. So set A to be A1. Okay. And B to be this B1 plus B2 minus A2. Okay. So I know what B1 and B2 and minus A2 are, so I can calculate this B. Not a big deal. Okay. You will also think over it that why the B it is actually. Why I am not just simply taking B2 as my B. Why I am not doing it. Ponder over it actually. So let's think over it together. Define. So take A to be A1 and B to be this number. Let me define what? Define a concatenated path. Okay. Concatenated path, which I am going to denote by P1 star P2. Okay? P1 star P2 is the concatenation of path P1 and P2 as a map from A to B into Rn, defined by, how it is defined by. So I want to treat this entire quantity as a single entity. So I'm going to say that this P1 star P2 is operating onto an instant t. If this instant t is a movement in the interval A1, B1, in other words this first interval, then this concatenated curve is same as this curve. Okay? So it's equal to P1 t. Alright? And if you take, say, t from the interval B1 to B, okay, then this curve is going to give you P2 evaluated at T minus B1 plus A2. Why this definition is the way that it is? Okay. Why this definition is the way it is? Think about it. If this curve is a true representation, okay, is a true representation of these two curves or the join of these two curves, then if I substitute any value here, it should give you the same value as whatever the B1 is giving. And if I substitute any value here in this interval, it should give the same value as P2 is giving you. Okay? So let's think over it, that whether this gives the same value as P1 and P2 or not. So the first part is evident. This is part of definition actually, that if you are taking a T between A1 and A2, you are getting what? P1 of P1 of D actually. So there is no trouble in it. The real thing would be to think over it. Let's evaluate this concatenated curve on this A2, which is same as B1 actually. So let's think over it. So what would be the P1 star P2 evaluated, say, at A2? So this would be same as P1 star P2. If I evaluate it at, for example, B1, this would be same as P2 of B1 minus B1 plus A2. So isn't that same as P2 of A2? That's what we wanted actually. Okay? That P1 star P2 evaluated at B1, okay, which is same as A2, should give you what? P2 of A2, but I know that this P2 of A2 is same as P1 of B1 actually. Okay? There is no trouble with that. समझ आ रही है बात? थोड़ी सी. Let's think about its other endpoint actually. So what is the other endpoint? So B. So if I evaluate this concatenated curve on B, am I going to get P2 of B2 or not? So if I am getting B2 of B2, the formula should seem fine actually. So if I compute, for example, this concatenated curve at a point, for example, what point? B, okay, which is the other end point of the curve. Okay, so what this would be? So this would be P2 of B minus B1 plus A2. And what is B?
So B
is, this guy. So substitute this B into it. P2, so you're going to get what? B1 plus B2 minus A2 minus B1 plus A2. Okay, so what is the net result?
P2 over B2.
You get P2 over B2. So now you can see that why you are choosing this number. You are choosing this number so that it should agree, with this intuition. So, I mean, if you see, so if I have a curve, for example, f of x, and I'm subtracting something out of it from the input, so how does, what change would, this is going to give actually on the curve? क्या change आएगी? Right, left side?
Sir, right hand side.
Left. So if I add, for example, this 2 from outside, what will happen? Move up and down. और -2 का मतलब क्या है? So move on to the right actually. So what you are doing actually. So you are taking t's from this interval, okay, from this interval, and then shifting the outputs onto the right of what? Right of the A2. Okay, right of the A2. So that's what we are doing out onto the right of this curve actually. It's pointing it right, but we are kind of shifting it. Okay. You can take this generically. So take t from, so if it's still in the confusion. So take any t between b1 and b. Okay. So take a t between b1 and b. So b is what? Let me substitute its value. So it's b1 plus b2 minus a2. Right? You have it. And now in this t, subtract b1 and add a2. Subtract b1 and add a2. So when you're going to subtract b1, this will go away and add a2, so you're going to get a2. Okay? Less than or equal to t minus b1 plus a2. So what you're going to get on the other side? So subtract b1, this will go away, add a2, this will go away. So this is a valid input in the domain of p2. Therefore I can operate it. Okay? And I know that since this, input is in the domain of p2, it's gonna be a point here. It's gonna be a point here. Are you getting the point? So it's just a trick actually. It's just a trick. So the two things that you have, now you want to see them as a single quantity. Okay? So this definition works. It works. Let's do a concrete example. Okay? Let's do a concrete example and let's concatenate two curves. असल कॉपी भी जो है समझ नहीं आया असल थोड़ा आ रहा है so you should convince yourself that why you should have this expression here. Okay? Why you should have this expression? Because if you don't have this expression and you just substitute any t between b1 and b, then outputs are maybe outside of the domain of the p2. So subtracting b1 and adding a2 is like making sure that you are in the domain of p2.
So when we combine two curves, is it necessary that they both should have the same orientation?
This is a good point. I mean, imagine if I have a curve, okay. We need to, put one curve, okay, like these two curves as a single curve actually. Now imagine if a curve, if you combine them, but it has two parts and both parts have opposite orientation. So what are you going to say about the orientation of this bigger curve? So, it will not be well defined actually. So it should have one orientation. So imagine I have a curve, another curve which has, an opposite orientation to the first curve, for example. Then you're going to do what? You're going to take one curve and reverse it. Then that reverse curve, so imagine this curve has an opposite orientation and you want to concatenate these two curves. So what you're going to do, you're going to take one curve, for example this curve, and reverse its orientation. I know how to reverse the orientation. And now concatenate the original curve and this reverse curve. And that is going to be a curve that has a well-defined orientation actually. Are you getting the point? So you have to look for the orientation as well. So here's an example. So imagine I have a curve, I have a, a circle that has two parameterizations. Cos t, say